So, in the previous class we introduced the notion of Sobolev spaces, and we also saw some simple properties for the weak derivatives to be again in this integral class. Okay, so one of the aims of this study of Sobolev spaces is that we want to extend this integration by parts in higher dimensions. Okay. So, if u and v are C1 in omega bar, okay, then under certain conditions on the boundary we have this integration by parts. So, u dv by dxk is u v, I will write nu k, this is ds, okay, minus again over omega v du by dxk. Okay. So, the first one and the last one are volume integrals, and this is boundary integral. So, this is volume integral and this is boundary integral. And this we call surface measure on del omega. And nu is just nu 1, nu 2, nu n is the outward unit normal to del omega. Okay, so, here is the picture. So, this is omega and this is del omega. So, you pick any point here. So, of course, it depends on nu depends on the point. So, this is nu. Okay, so, it okay, so, here in order to define this surface measure and this continuity of the unit outward unit normal. So, we require certain conditions on the boundary that will come little later, but as of now suppose you want to extend this formula for integration by parts. So, our main aim, okay, main aim extend this formula for, so we need only one derivative here. So, just u v in h1 omega. Okay. So, of course, even for the smooth functions we do require certain conditions on the boundary. Of course, those same things will also assume that there is no problem for that. The problem comes okay. So, here there is no problem again with respect to the volume integral, because u is in L2, okay, and this is also in L2. So, this makes sense. and same thing here, B is in L2 and del U by del x k is in L2 because we are assuming uv in H1 omega. So, there is no problem. Okay. But what meaning do you give for uv on the boundary? So, here we do not know how to define u and v just because u and v are in H1 omega. How do we assign value of u and v on this del omega, and in what sense, and whether this is integrable with respect to the surface measure. Surface measure comes only by putting some conditions on the boundary. Okay. So, that is nothing to do with these functions in H omega. So, that how do we interpret this surface integral and how do we interpret these values of u and v on del omega. Okay. So, our discussion on Sobolev spaces is mainly on this issue, and so if we can give a meaning of u and v on the boundary and show that, for example, if we can show, okay, so that's, so if C1 omega bar is dense in H1 omega, okay, so certainly we can extend the volume integrals, but this surface integral still remains a question, but that we can handle after assigning so what we call the trace of uv on, they are defined on del omega, and they are all L2 functions with respect to this surface measure. So, everything goes through smoothly, but the important thing is we have to prove this. Okay. Then there is a way. There is a way to extend this formula for H1 omega functions. Okay. So, that is our main concentration. Okay. So, we all developed the theory of Sobolev spaces with this in mind, because this is going to be used very often in the second part of this course. Okay. So, pay attention to this and learn it carefully. Okay. So, more generally we show that Cm omega bar is dense in Hm omega. That is our next goal. Okay. So, in this direction, so I will just write some observations regarding. As I said, I am not going to prove many things, some are very easy to observe. Observations on HMO. Okay, so you should be able to work out many of these things. So, if this is almost trivial, omega tilde is open, then Hm omega Hm. Okay. So, whenever inclusions are there, you also check the continuity. Okay. So, that is also important. Okay. So, if A is a Cm function and U is in Hm omega, then a u is also in HM. Okay. So, for example, the derivative, so this d alpha a u can be written down using Leibniz formula. Okay, so do it. It's not for example, suppose I want to show the first derivative, so I have to verify. So this omega, let me just make this a u and d phi by dxi, and this is where that observation comes into play. Okay, so this this is the definition. So, we want to see what this is. Okay. Want to find out what this is. Okay. If I want to show that AU is also in HM. So, this is where that important observation comes into play, namely that it is sufficient to take phi only up to order m. So, Cm with compact support. Okay. So, this, let me just, in order to find that thing, let us go here. So, this is omega u a d phi by dxi okay. And so this is Cm only. So, this is also fine up to Cm is there. Okay. So, this I write it as u d by dxi, because A is smooth. So, I can write that. So, this is the usual derivative. So, just distinguish between the classical derivative and weak derivative. Okay. The first part, since A phi is also a Cm function, so the first part gives me minus du by dxi A phi. Okay. And the second one I write it as minus dA by dxi u pi. Okay. So, everything on omega. Okay. So, now this also you can write it as A du by dxi. So, finally, we do get d by dxi as AU as, see, it looks so similar, but this verification has to be done. Okay. So, this is in L2 and A is a smooth function and omega is bounded. So, this is bounded. So, this is also in L2, and again for the same region this is bounded and this is in L2. So, whole thing is in L2. Okay. Such verifications you should be doing all the time. So, the third one, third observation, Okay, so just if u is in Hm omega and omega tilde is open and whose bound closure is also an omega. So, omega tilde, let me just, is compacted because omega is bounded. Okay. Then u epsilon minus u Hm omega tilde. So, I am not claiming that this tends to 0 as epsilon tends to 0. So, again as usual this u epsilon modifiers. Okay, so, these are C infinity functions. In fact, let me just write that Cm, you can, they go up to there. Okay. So, observe that we cannot do directly to omega, but if we remain, okay, so this is omega here and any compact set. So, this is omega tilde. Okay. So, as long as that omega tilde stays away from the boundary, okay, that is important. Otherwise, we have got already density result, okay, but this is not. So, we want this to happen, may not be for the modifiers, but some Cm functions, but we want to go up to omega. Okay. So, this omega tilde you want to replace it by omega, and that is hard part. Okay. So, the replacing omega tilde by omega and u epsilon by some other Cm functions require lots of technicalities. Okay. So, that will develop. Okay. So, if you are just want some compact subset, then the modifiers will do the job for us. Okay. But this is not really the density result we want. We want the Cm omega bar to be dense in Hm omega, not omega tilde. Okay. So, here what we are seeing is it is dense in Hm omega tilde for any compact subset of omega. Okay. So, that is the extension we are seeking. Okay. And again, when we are working with this compact subset, things are somewhat easy, okay, but we want them to happen in omega. So, if u in Hm omega has compact support, this you have seen many times, this how this compact support helps us, then by extending u by 0 outside its support, This you have even seen for the distributions. Outside its support, we see that u is in hm omega tilde for any omega tilde containing omega. Okay. So, this is very important, very important. In fact, that is one of our requirement. We will soon do that. We want to extend any hm omega function u to a larger domain. Okay. That we cannot do this easily. Okay. So, when it has compact support, we can just extend it by 0. So, there is absolutely no problem. But when it does not have compact support, again it is a technical result. We will do that. Okay. Okay. The next observation, there are several things. So, this is essentially change of variables. Okay. So, this we need when we want to work near the boundary. Variables. Okay. So, suppose omega 1, omega 2 are bounded regions. So, essentially we want to an hm function which is defined in omega 1, we want to get a function hm function again in omega 2 and vice versa. Okay. That we can do when this omega 1 and omega 2 are in 1 correspondence. Okay. So, let me just this is change of variable. So, y from omega 1 to omega 2. So, since we are in n dimensions, so let me write that y1, y2, yn, and each yi is a function of x1, x2, xn, and x is in omega 1. Okay. B 1 1 on 2, and so this is smoothness we want, because we want hm functions to go into hm functions. So, this each yi belongs to Cm omega 1 bar. Okay. Then there is a mapping from hm omega 1 into hm omega 2. And using the inverse transform, we also see that there is a mapping from hm omega 2 to hm omega 1. So, how we describe this? Okay. So, first let me in fact start from here and then come back to so variables. Okay. So, I stress the variables. So, h u y belongs to hm omega 2. Okay. So, define u from omega 1 to r or c, okay, whatever real valued functions or complex valued functions, by u of x is equal to u of yx. Okay. Then of course this chain rule you have to use. So then this u belongs to hm omega 1. So use chain rule, you get that. And that's where the assumptions come into play. Okay. Further, this is important for us. This u hm omega 1 is less than or equal to constant u hm omega 2, and also have the reverse one, hm omega 2 omega 1. These constants essentially come from the bounds of the Jacobian. Okay, so if you just recall the change of variable formula, let me just, okay, so this omega, any function, any integral function, so this y dy is equal to integral f of yx. So Jacobian comes, right? So Jacobian of the transformation. Okay, so when you want to estimate any such integral, so if these are bounded, so that those result in the C1 and C2. Okay, so the constants come from that essentially. So this you apply for u and all its derivatives. Okay, so that's and let me just this. Okay, so let me just state this. Okay, this simple extension result. So here geometry is simple and we can make use of that. Okay, so this, so I am going to consider this rectangular parallelepiped so pi a, I just write that. So this is x in Rn action such that mod xi is less than a. So this a1, a2 are some finite positive real numbers. Okay. then this is first density, not extension, density result. Density result. Then Cm pi a bar is dense in Hm pi. Okay. Let me just sketch in next few minutes and then we will stop there. So, okay, so sketch. So how this spatial geometry helps us to do this somewhat easily compared to a general domain. Okay, so that will come in the subsequent lectures. Okay, so let f belongs to Hm pi a and alpha is a multi-index. Okay. So, given any epsilon positive, there exists phi alpha. So, this is just continuous. Okay. This is such that d alpha f minus phi alpha in L2 pi a is less than epsilon. Because we know that continuous functions are dense in L2, that is what I am just using. Okay. And now next what you do is you slightly extend this parallelepiped. Okay. So, for sigma bigger than 1, you put pi a sigma here now just you put a I sigma. So, slightly larger one. Okay. And define f sigma is f sigma of x is f by f sigma. Okay. So, this is for x in pi a sigma. So, now f sigma is defined on a slightly larger domain, and this is a very simple transformation. So, from pi a to pi a sigma. So, that earlier property, I think number 4. So, this f sigma is Hm pi a bar pi, certainly pi. Okay. So, stress that pi a is a subset of pi a sigma. Okay. And then okay, let me quick skip few steps here. Okay. So, what you finally using this f sigma, this. So, okay, after some computations, as I told in the beginning, these are not hard, but okay. So, what we really get is d alpha f, this is the one we started with, and d alpha f sigma again in L2 pi a. Okay. So, this have carefully done. So, some constant times epsilon, that epsilon we started with. Okay. And since there are actually you require this each sigma is different for different alpha. Since there are finitely many, we can choose the smallest one. So, okay, so let sigma 0 be chosen. It works for all alpha such that d alpha f minus d, let me write why all the, okay, let me write that d alpha f sigma 0 in L2 pi a less than c epsilon for all alpha, and that implies, so we can write f minus f sigma 0 in hm pi a c epsilon. Okay. And now you replace approximate. So now we are slightly larger domain, approximate f sigma 0 by its modifiers. F sigma 0 epsilon, and these are C infinity functions. So, in particular CM functions, and those modifiers will approximate the f. Okay. So, how the simple geometry helps us to, first of all we are extending. Okay. So, that is one important step here. We are extending the given hm omega function to a larger domain, and then we are using modifiers. Okay. So, there are two steps here, and this is the procedure we are going to follow for the general domain, and that we will take up in the next class. Thank you.